Hello guys, welcome to 2.1. We're looking at instantaneous rate of change. Now, before we get started with the slides, I just want to give you guys, I want to say a quick review slash introduction. So first, we know how slope works, right? Slope, or the letter M, is given by y2 minus y1 over x2 minus x1. Right? Or rise over one, as we know it. So, slope measures how steep a line is, right? Right. For example, if it's going up, it's positive, right? If it's going down, then slope is negative. And if you're looking at a flat line, then the slope is 0, right? Okay. So here we are introducing another name for slope, which is called the rate of change, right? So rate of change is just you can think about it as a fancier name for slope, and actually it's uh, mostly used in terms of application. Right? Rate of change is given by the change in y values over the change in x values. Okay? So this is basically what a rate of change is, and we're looking at something called the instantaneous rate of change. And let's take a look at our first example. And we're not actually going into the material yet. All right, there we go. So let's take some time and look through this table together. All right, so table 2.1, what we have here is time versus feet, right? We are throwing a grapefruit upwards, and then after time, this many seconds, it tells us how many feet above the ground the grapefruit is. So at 0, I want to draw something here as well. So let's say t equal to 0. We are at right here, right? That's the grapefruit, and maybe this is the ground. Right? T equal to 0, right? And 6 feet above the ground because probably it's maybe on something, or maybe someone is holding it, right? So 6 feet. I'm just gonna mark it 6. All right, and when t is 1, meaning 1 second after it, the grapefruit is right here, right? 90 feet above the ground. All right, so here is something we can think about. Okay, at time 0, it's 6. At time 90, at time 1, we have 90 feet above the ground. So how fast did the grapefruit shoot up in the air so it gets to 90 feet above the ground after 1 second, right? And this is what we can do using the formula, right? Delta average velocity formula right here. It's given to you. The displacement in distance over the displacement of time, right? So average velocity is 90 minus 6 over 1 minus 0, right? So about 84 feet per second, okay? And I want you guys to think about this number, 84 feet per second. Does that mean the grapefruit is traveling at a constant speed, which is 84 feet per second? That is very unlikely, right? Because maybe the grapefruit has somehow it has to gain speed, and then if it's traveling in the air with nothing else pushing it, then it's going to lose some speed, right? So from between the time 0 and 1, it's the speed is actually not the same at every millisecond. Okay, so this 84 feet per second, that's why we call that the average velocity. On average, how fast is the grapefruit traveling? Right? We can say 84 feet per second, but that does not mean it's actually a constant speed for the grapefruit at any time given between 0 and 1. right? So instantaneous rate of change, which we'll look at shortly, is exactly, let's say, at 0.443 second, what is the speed of the grapefruit, right? And that is what we want to estimate. Okay, and let's look at the example right here. All right, so here we are looking at the average velocity between 1 and 1.01. Right? So they actually come up with a function and say, okay, at 1.01, the distance, the height is 90.678, and then subtract 90 divided by the time difference, which is 0.01 second, and then we get 67.8 feet per second. Right? And again, that's just an average velocity. That's a guess. And on average, how fast was the grapefruit traveling between time equal to 1 and 1.01. Right? So here is the main question. How can we find the velocity at exactly t equal to 1? Okay, and that's the question we have to ask and we have to answer. All right, now this next table shows you a different average velocity depending on which the time that you're looking at. For example, between 0 and 1, that's 84, right? Which that's the one we found. And between 1 and 2, it's 52. But if we shrink the time gap, for example, from 0.9 to 1, it becomes 69.6. If we shrink it more, 0.99 to 1, it's 68.2. And if it's 0.999 to 1, it's 68. Notice that it's decreasing, but it's decreasing slower, right? Let me show you what I mean by decreasing slower. Right, so going from here to here, when we shrink the time gap, we closed about 14 feet per second, right? But going from here to here, we closed 1.4 feet per second. But again, we get 0.2 feet per second, right? So we're actually getting very close to the actual speed at time 1, right? For example, if we enter another one, let's say 0.9999, 0.9999, right? It's going to be very close to the actual speed, right? Which we don't know what it is. Right? So in this idea of closing the gap, closing the time gap, will give us a more accurate estimate of the actual speed when time is equal to 1. I should say velocity, when the actual velocity when time is equal to 1. Okay. All right, so here we have some definition. Let's just go over this a little bit. I mean, they're just definitions. Instantaneous velocity of an object at time t is defined to be the limit of the average velocity of the object over shorter and shorter period of time. All right, that's what we were doing. Instead of using 0 to 1 and then 0.9 to 1, we use 0.99 to 1 second and 0.999 to 1 second. Right, we're closing the time gap to find the instantaneous velocity. All right, now to again to a more general idea, instantaneous rate of change of some function f at the point A, also called the rate of change of f at A, is defined to be the limit of the average rates over f over shorter and shorter intervals around A. And that is also called the derivative. The derivative at a point is written as this: f prime of A. This little dot here is red prime, right? So let me write a note here. This is f prime of A. Okay, it's defined to be the instantaneous rate of change of f at the point A. Okay, so let's look at this page together. So let's look at the first graph. So the black line here, so we have the blue curve, which is the function f, and the black line, that is just a straight line going through the point A and B, right? So when we can calculate the slope of this line between A and B, and that also gives us the average rate of change between point A and B, right? So when we are talking about average rate of change, we are only talking about the x values, right? So the rate of change between x equal to a and x equal to b is the slope right here, or the average rate of change. Okay, now, in order to get a better, I shouldn't say better. Let's say I want to find the rate of change at point A, the exact rate of change at point A. This line wouldn't be that accurate, right? So what we do is we can close up the point, right? Instead of using the point here, instead of using this B, I'm going to use this little b, right? And then we can close the gap, make the 2 points a little closer. So if you look at the gray lines right here, you can see that as we move point B closer and closer to A, the gray line becomes flatter, or I should say close to the behavior of the line at A, of the line at point A. Okay, so eventually what we are actually interested in is the rate of change at a point. Let's say I want to pick this point A. The rate of change right here is the same as the slope of the line passing through this point only. So I'm going to attempt to draw a flat line that only goes through the point A. All right, here we go. Okay, so I drew this green line through the point A on the graph without touching anything else on the white line, right? The green line, the intersection between the green line and the white line is the point A, right? Nothing else. Then the slope of the green line is equal to the rate of change at point A. Okay, but think about this. If we want to find the slope of a line, we need at least 2 points in order to use the formula, right? The rise over one. But here, since we only have 1 point on the line, which is the point A, so how do we find the rate of change at exactly 1 point, right? And that opens up the ideas of calculus, and that's what we're going to learn in this chapter. Okay, so let's do a little warm-up practice with slope. Right, so we're given 6 points. We want to find out whether the slope at the point is positive or negative or maybe 0, and which graph has the greatest slope, the least slope. Right, so go ahead and actually I want to do one of them with you guys. Let's say I want to do point F. So point F, I want to draw a straight line that passes through only F and not anything else. So it's a little hard, but you don't have to be very accurate. Let's say this line right here, right? The red line. Okay, so I mean at point F, this line it's going down, right? So that means I have a negative slope, and it's pretty steep. So I would say it's a pretty large negative number, right? So go ahead and try the others. Pause the video and try the others on your own. All right, so you don't have to be very accurate, right? Let's start with point A. So that's going up, so I would say that's positive, right? This is almost flat. I want to say it's flat, right? I just say it's 0, and that's negative. That's going up, right? So you're always traveling to the right, right? So that's positive, and this is flat. That's 0. Okay, so at which label point does your graph have the greatest slope? Most positive, right? So that means it's increasing the fastest. So you look at the increased one, it's A or D, right? I want to say A is maybe increasing a little faster, right? So greatest slope, A. The least slope, negative with the largest magnitude, right? So I want to say it's F, right? F is decreasing the fastest, right? Okay, so that's just some warm up. of identifying slope and finding that slope at a certain point. All right, so here we have another example, problem 23. Let's look at this together. The table gives capital P is equal to F of T, the number of household in millions in the US which cable television T years with cable television T years since 1998. So let's look at two parts. Does F prime of 2 appear to be positive or negative? What does this tell you about the number of household with cable television? Estimate F prime of 2, estimate F prime of 10, and explain what each is telling. Okay, so before we move on, remember that F prime, let's take a look at part A first. F prime of 2 means the rate of change at t equal to 2. Oops, not 0, 2. Okay, so in the context of this problem,